Hello and welcome to our webcast. Today's topic will be underfloor air distribution. My name is Randy Zimmerman and I'll be presenting today's program. I'm a chief engineer at Titus with 32 years of HVAC experience. I'm also the vice chair of ASHRAE TC 5.3 that covers all types of room air distribution, including underfloor air distribution. First off, let's start calling it UFAD to save time and syllables. Although they were originally only used for specialized cooling applications such as computer server rooms in North America, about 15 years ago, UFAD systems found their way into office buildings. Today's webinar will cover all aspects of UFAD, including a system overview, specialized system components, design considerations, and how these systems can be utilized to achieve LEED credits. Now let me give you my standard disclaimer that I make whenever I cover only one type of system in a presentation. It's not my intent to sell you on a particular system. Most systems have a distinct advantage of one kind or another, but every system has its limitations. There's no system that's the best choice for every application, but knowledge of each technology will assist you to make the right design decisions. So now let's talk about UFAD. Why might we want to use a UFAD system? There are many reasons why UFAD has grown in popularity. A properly designed and operating UFAD system can provide improved thermal comfort and ventilation effectiveness while saving energy at the same time. UFAD systems are most frequently used in open-plan office environments, allowing workspaces to be reconfigured quickly with minimal disruption and cost for the tenant. It's easy to make claims such as these, but let's dig a little deeper and see how UFAD systems can actually deliver these advantages. First of all, how do we define thermal comfort? Well, ASHRAE Standard 55 defines thermal comfort in terms of local air velocity in the occupied zone and temperature stratification. Excessive air velocity creates a feeling of draftiness that we sense on our skin. As a general rule, velocities above 50 feet per minute in the occupied zone are to be avoided in cooling situations. During heating, we are more sensitive to draft, so we need to keep velocities below 30 feet per minute. Stratification usually carries a negative connotation, but if we're careful and control the level of stratification, we can use it to our advantage when designing UFAD systems. You know that you have excessive temperature stratification when you sit down and feel cold, but stand up and feel like you've got a fever. This is a common situation in poorly designed overhead heating applications. Standard 55 recommends no more than a 5.4 degree delta T between the neck and ankle region of a standing person. This translates into a 3.6 degree Fahrenheit delta T for a seated person. So long as we can limit velocities and stratification in the occupied zone, we should be able to deliver good thermal comfort. Now let's look at ventilation. ASHRAE Standard 62.1 defines the requirements for acceptable ventilation. It sets the minimum requirements in order to create healthful conditions for human occupancy with regard to ventilation. This standard spells out exactly how many CFM or air changes need to be provided based on occupancy, activity, or square footage, and how much fresh air should be provided. Anyone who understands air distribution knows that it's not enough to simply deliver air changes to a room. In order to be effective, fresh air must reach the breathing zone of the occupants. ASHRAE Standard 62.1 also rates various types of air distribution systems with respect to zone air distribution effectiveness, or EZ. Ventilation air is only effective if it reaches the breathing zone of the occupants. Therefore, systems can be rated for ventilation effectiveness based on the location of the outlets, the returns, and the temperature of the supply air. Table 6.2.2.2 in the standard provides EZ values for various systems and conditions. For instance, supplying cool air from the ceiling has an EZ value of 1. This means that if the minimum ventilation requirement for an office environment is 5 CFM per person, The system must deliver at least 5 CFM per person. If the same space were supplied from a floor plenum using low-velocity diffusers with a vertical throat of 50 feet per minute equal to or less than 4.5 feet, the EZ value would be 1.2. Anytime the EZ value is greater than 1, the amount of ventilation air is reduced. Likewise, anytime the EZ value is less than 1, the amount of ventilation is increased. For the low-velocity floor supply, the ventilation per person could be reduced by 17% because EZ equals 1.2. I should point out that this reduction in ventilation may not comply with local code requirements, so check first with local officials. Now let's look at conventional overhead systems to see how UFAD systems differ in design and operation. In order to explain the advantages of UFAD, we first need to understand conventional overhead systems. ASHRAE defines typical overhead systems as being fully mixed. This means that ideally an overhead system creates its air pattern outside the occupied zone with enough discharge velocity to generate low velocity room air entrainment to promote thorough mixing with the room air. Conventional overhead systems are classified by ASHRAE as fully mixed systems. Supply air is delivered from ceiling diffusers or high sidewall grills. In theory, this type of system is intended to create nearly uniform temperatures from floor to ceiling through thorough mixing of supply and room air. The diffusers or grills should be positioned, sized, and selected for air patterns that will prevent any velocities in excess of 50 feet per minute in the occupied zone. By keeping high velocities safely away from occupants, comfort is maintained. Meanwhile, the high velocities on the ceilings and other room surfaces create low velocity room air entrainment, resulting in improved air circulation and thorough room air mixing. Systems that deliver air from overhead typically supply cooling at 55 degrees Fahrenheit. This is necessary because in order to deliver cooling to the occupied zone and ventilation to the breathing zone, the supply air must first break through the layer of warm air at the ceiling. This layer of air is formed due to the increased buoyancy of warmer room air, often containing higher concentrations of pollutants and contaminants, and the heat from lighting systems. Since this heat will be picked up immediately by the colder supply air, its temperature begins to rise as it discharges from the supply outlet. As this slide shows, like most systems, overhead systems typically condition spaces with multiple occupants. Since people often have different preferences when it comes to thermal comfort, it can be challenging to keep everyone satisfied and productive when spaces are served by a single thermostat setting. UFAD systems are different. So if a conventional overhead system is classified as a fully mixed system, how would a UFAD system be classified? Well, there are systems that use displacement ventilation that are classified as fully stratified systems. UFAD systems have much more in common with fully stratified systems than fully mixed systems, but they aren't fully stratified. While it's possible to design a UFAD system to be fully stratified, most UFAD systems function as partially mixed systems. Since the UFAD system is delivering air directly to the occupied zone, care must be taken so as not to create excessive velocity and associated comfort problems. For this reason, special types of floor outlets have been developed for use in UFAD systems. We'll look at these in detail later in the program. Another thing that we'll do to prevent thermal discomfort is to deliver cold supply air at a higher temperature than an overhead system. Instead of 55-degree air, UFAD systems typically supply at temperatures between 60 and 68 degrees Fahrenheit. I find that 65 degrees is pretty common. These higher temperatures are possible because the supply air no longer has to handle the heat layer that forms at the ceiling. This heat is still removed and is therefore part of the HVAC equipment load, but it is no longer part of the supply air load. As this slide shows, UFAD systems often employ smaller outlets to deliver supply air to the occupants. This is possible because no additional ductwork and associated cost is required. Since the occupants are less likely to share an outlet, and many of these devices provide a means of user adjustment, comfort can be less of a challenge. Now let's look at the components found in a typical UFAD system. The basic components of the raised floor system can be seen in this picture. UFAD systems in North America typically use 2 foot by 2 foot square floor panels. The floor panels are made from composite materials and are most commonly made from steel panels filled with a concrete-like material. The panels are supported on their corners by steel pedestals. The pedestals are adjustable and typically create floor plenums 6 to 18 inches tall. Some systems use stringers and others mount the panels directly to the pedestals. Sometimes horizontal stringers and additional diagonal bracing may be required to create plenums greater than 18 inches tall or to meet seismic requirements. Devices that can't fit between the pedestals with the standard 24-inch pedestal spacing will typically require bridging to support the floor panels. The floor panels are available without openings or with a variety of pre-punched holes to accommodate floor-mounted air outlets and wiring grommets. The height of the floor plenum is often determined by factors other than airflow requirements. There must be sufficient space under the floor to fit ductwork, plumbing, electrical, and data wiring, etc. Although it's possible to achieve uniform pressure and airflow distribution in a UFAD plenum in as little as 4 inches, it's rare to see a plenum less than 12 inches tall. The most popular floor plenum height is 14 inches. The floor panels are typically covered with carpet squares. These carpet squares are available in many sizes. Some are installed with adhesive and others are magnetic or dimpled to hold tight. There are a variety of opinions regarding the best carpet strategies. Using a single carpet square on each floor panel may allow easier access below the floor, but carpet that overlaps the floor panel seams may help control air leakage. There are other opinions based on the ease of cleaning and in ways of reducing wear. The best thing to do is talk to carpet vendors to find out about the latest products and technology before deciding on what you're going to use. Here you can see how the floor pedestals look when they're installed with a standard 24-inch spacing. But that's enough about floor products. Let's get back to air distribution. So where does the supply air come from? It comes from an air handler, of course. The air handler could be located in an equipment room inside the building, or it could be located on the roof. Cold supply air will be ducted into the UFAD plenum, and return air will be ducted back to the air handler from the ceiling. In UFAD systems, it's preferable to locate return grills in the ceiling or high side wall. This takes advantage of the natural buoyancy of warm air to rise and exit the room. As in conventional systems, return grill locations don't have any effect on actual room air motion. In effect, return grills merely provide a means for air to escape the room. The higher supply air temperatures and lower supply air volumes in UFAD systems result in higher return air temperatures than those of conventional overhead systems. The higher return air temperatures are also a result of having loads created by ceiling lights carried away by return air before ever mixing with room air. You might expect the depth of the UFAD plenum would be strictly dependent on the expected room loads and associated air volumes, but that's not necessarily true. The height of the floor plenum is often determined by factors other than airflow requirements. There must be sufficient space under the floor to fit ductwork, plumbing, electrical, data, etc. Although UFAD systems have less ductwork than overhead systems, there will be ductwork. The size and shape of the building footprint determines the amount of underfloor ductwork that will be necessary. Supply must be delivered in such a way that equalizes the underfloor pressure. The larger the floor plan, the longer the ductwork must be to deliver air to the perimeter zones. The ducts that supply the air to the plenum create so-called injection points. As a general rule, UFAD diffusers should never be located further than 30 feet from an injection point. It should also be noted that UFAD diffusers should not be any closer than 6 feet from an injection point. Fast-moving air passing below a diffuser could easily turn an outlet into an inlet. So we need to make sure that we don't induce room air into our diffusers. But what about pressure? The static pressure in a UFAD plenum can range from 0.05 inches to 1/10 of an inch. The most common operating pressure seems to be around 0.07 inches. Now, 1/10 of an inch might not seem like much pressure, but when you apply it to the entire square footage of a building floor, it is sizable. Most UFAD systems operate below this pressure because it's simply not possible to maintain that pressure. With air exiting from UFAD diffusers and leakage around floor panels and walls, pressure is lost. Unlike a conventional overhead system, where duct leakage is lost to the ceiling plenum, in UFAD systems most of the leakage still finds its way into the occupied space. Another thing to consider involves underfloor zoning. If more air is needed in a particular part of the floor plan than the UFAD plenum could normally supply, sometimes it makes sense to create underfloor partitions. Air can be ducted directly to these partitioned areas to ensure that adequate volume at low enough temperature will be available. Obviously, this partitioning adds cost and makes the spaces less flexible for future reconfiguration. In this slide, you can see both an injection point and some zone partitions. Notice that the discharge of the injection point has been fitted with a grill. There are a number of manufacturers that offer grills specifically for this purpose. If you look closely, you can also see how the zone partitions have been notched and sealed to go over conduit, plumbing, and other obstructions found beneath the floor. Sometimes partitioning is necessary to limit supply air temperature rise. As cool air from the air handler moves across the UFAD plenum, it is in contact with the floor panels above and the concrete slab below. In a multi-story building, the slab is also in contact with warm return air from the floor below. This tends to heat the slab, and this in turn warms the supply air going to the floor above. This is the reason that injection points need to be no further than 30 feet from the furthest diffuser. This limits the supply air temperature rise. Air ducted to partition zones doesn't experience this temperature rise. There are other strategies that can be employed to reduce supply air temperature rise besides partitions. These include insulating the underside of each floor slab in a multi-story building, isolating the floor slabs from the perimeter walls, selecting floor panels with high thermal mass and low thermal conductivity, and using more ductwork to get within 30 feet of the furthest diffuser. Now let's look into some popular misconceptions about UFAD systems. These three topics are frequent concerns for designers and building owners who are considering UFAD technology. They include leakage, humidity, dirt, and spillage. Leakage is an issue for any UFAD system. The amount of leakage is dependent on the quality of workmanship and the level of planning that goes into the design. It's easier to design and specify for low plenum leakage than it is to go back after the fact to remediate. In this diagram, you can see some of the most common problem areas. These include leakage around floor panels, through floor coverings, through conduit, and around floor edges. This diagram shows additional problem areas. These include leakage through data boxes, through electrical boxes, through wall penetrations, and at perimeter walls. Leakage can be the biggest problem for the efficiency of a UFAD system if it isn't handled properly. UFAD systems require a certain level of expertise for all of the construction trades. Contractors without previous experience with UFAD systems are likely to underestimate the cost of minimizing leakage. Walls and stair landings can contribute 10 to 30% of total leakage if not sealed properly. Overlapping carpet squares over floor panel seams can reduce leakage by up to 50%. Regular inspections during the course of construction are necessary to prevent plumbers, electricians, and control contractors from punching holes and failing to seal them properly afterwards. When sealed properly, UFAD systems operate very efficiently. Delivering supply air at 60 to 68 degrees causes some designers to fear issues with humidity. All systems, regardless of type, must hold relative humidity in a building to less than 60% to prevent IAQ problems. There are many possible strategies for reducing the moisture level of the supply air. These include condenser water reheat, runaround coils, or face and bypass arrangements. Many UFAD systems use conventional air handlers producing 55-degree air that is mixed with return air to raise the temperature. Cleanliness of the UFAD plenum can also be of concern to building owners. At the end of construction, the UFAD plenum is routinely cleaned of all dirt and debris. Most UFAD diffusers are designed to catch any accidental liquid spills before they can reach the concrete slab below. Unlike ceiling diffusers that generally discharge at high enough velocity to entrain and deposit dirt and dust on ceiling tiles, UFAD diffusers discharge at much lower velocities. Regardless of the system type, a certain level of housekeeping is required to prevent maintenance issues from getting out of control. Now let's look at the specialized HVAC devices that are used in UFAD systems. Supply air outlets for UFAD systems deserve special attention. Since the air will be discharging from the floor level directly into the occupied zone, it's important that floor-mounted outlets mix supply and room air as rapidly as possible, while both limiting vertical projection and creating the smallest area of velocity disturbance in the room. So-called swirl diffusers create a swirling air pattern in order to meet all of these requirements. Outlets of this type can be placed near occupants, in aisles, or just inside the entrance to a cubicle or a workstation. These outlets often include a user-accessible manual adjustment feature, allowing the occupant the option of increasing or decreasing the airflow delivered to their workspace. In larger shared spaces like elevator lobbies and reception areas, these same outlets are installed with outflow regulators to provide increased airflow. This next photo shows a line of swirl diffusers running along the length of a double row of more open workstations. They're a little hard to see because the gray color blends in very well with the carpet squares. For typical interior zones in an open plan office, one swirl diffuser will serve each workstation or 100 square feet. These diffusers typically handle 80 to 100 CFM each, with a throw to 50 feet per minute of less than 4.5 feet. Later we'll discuss why this is important. Since UFAD plenum pressures are always less than 1/10 of an inch, outlet sound levels are always very low. Swirl diffusers are available in several different materials. The most common material is polycarbonate plastic. There are different types of polycarbonate available from various manufacturers, and some are fire rated while others are not. Regardless of which type of polycarbonate is used, it's important that it is strong enough to withstand floor loading and foot traffic without cracking or chipping. In order to eliminate these issues, most manufacturers offer versions of their swirl diffusers in optional aluminum construction. The type of material selected for the swirl diffusers will likely impact the color and finishes that are available. Polycarbonate diffusers are typically available in standard gray and black, but some manufacturers can mold these products in custom colors if specified. Custom colors can be used to help the diffusers blend in with carpet colors, but building owners should buy additional inventory for future remodel work due to the relatively high cost of small batch orders. Aluminum diffusers are also available in various metallic or anodized finishes, but some manufacturers also have sublimated powder coat finishes available as well. These finishes can cover a wide range of simulated wood grains, marble finishes, and other appearances. Swirl diffusers are available with several common options. The first is a user-adjustable volume regulator. This allows the occupant of a cubicle or workstation to adjust the airflow for individual comfort control. The volume regulator typically consists of a basket positioned below the diffuser face. It often doubles as a bowl to catch any accidental liquid spills or debris that may drop through the face of the diffuser. The second option involves actuation. If swirl diffusers will be located where loads vary, such as perimeter spaces or conference rooms, it may be necessary to vary the air volume in response to a wall-mounted thermostat or controller. Actuated models are available from most manufacturers. They're typically powered by 24 volts AC and accept either a 0 to 10 volt DC input signal or a 24 volt 3-point floating control. Swirl diffusers are typically easy to install. Pre-punched floor panels are available in most common sizes. There is often either a clip or a mounting ring to allow for quick installation. These diffusers should be designed to install and remove from above without ever needing to gain access below the floor panel. Most manufacturers of UFAD diffusers also have available matching access floor grommets. These serve the purpose of providing a coordinated appearance and easy access to phone, data, and power connections beneath the floor. Most also provide blanking plugs or other devices to limit air leakage around smaller cables or through unused openings. There are also a variety of rectangular UFAD diffusers available. Some of these devices include plenums for ducted connections beneath the floor. Others include manually adjusted dampers for balancing or actuated dampers to provide VAV control. Some are designed to allow the diffuser to receive air from multiple sources. For instance, a plenum with an actuated damper could be ducted to an underfloor terminal unit for heating or receive cool air directly from the floor plenum. Some of these devices have lay-in grills that can be turned in various directions to create different air patterns on the floor or to direct air vertically for perimeter applications. Perimeter heating cannot be handled by the same UFAD devices used in interior zones. Perimeter heating is best handled by fan power terminals, radiant panels, or hydronic fin tube heaters. Series fan power terminals are sometimes used in UFAD systems, and many manufacturers offer a special model designed specifically for these applications. They're typically used in any occupied areas where loads may vary, such as perimeter zones and conference rooms. They typically provide an ECM to boost airflow to the desired location and a primary air inlet with a volume damper and velocity sensor. A digital VAV controller typically manages the operation of the unit. The primary inlet can be ducted to a supply air duct under the floor, or it can simply draw in air directly from the UFAD plenum. Sometimes the induction port is ducted to a floor grill or a return plenum. In some cases, the induction port may be blanked off or fitted with a motorized damper. These units are typically used when it's necessary to boost airflow and control the mixture of supply and return air to the space. These units are often available with optional electric or hot water reheat. This photo illustrates why special products are required for UFAD systems. These series fan-powered terminals were designed to fit between pedestals spaced 24 inches apart. Not only should the products fit properly, they must also be designed for service access from above. The unit in the photo has electrical enclosures that nest between the pedestals and separate access doors for the motor blower assembly, primary damper, and optional filter access. Terminal units are typically designed for zero maintenance, but they will eventually need to be repaired at some point in their life cycle. Another type of UFAD terminal unit is known as a booster box. These units are fan coils specifically designed to fit into UFAD floor systems. Unlike the series fan-powered terminals, the booster box typically has no damper to control the supply air mixture or volume. It simply draws air from the floor plenum and then is ducted to supply grills in the floor. The air volume control of the booster box is handled by modulating the speed of the ECM in response to a wall-mounted thermostat or controller. These units typically include either electric or hot water heat. And here you can see a typical booster box installation. Before we can address perimeter heating loads, it's important that we understand what we need to do from an air distribution perspective. Our UFAD system is creating limited stratification in the occupied zone for good thermal comfort and taking advantage of the natural buoyancy of interior heat from people, office equipment, and lighting to rise and leave the room. Therefore, it's critical that any perimeter heating solution that we employ must not interfere with the interior system. Any UFAD outlets located on perimeters need to create a vertical air pattern that provides coverage on exterior walls and glass, but the vertical projection should never exceed the height of the occupied zone. In our partially stratified system, heat and pollutants form a layer above the occupied zone. If the perimeter outlets break through the stratification layer, heat and pollutants are likely to be drawn back into the occupied zone, thereby defeating the purpose of our UFAD system. In this smoke video, you can see a properly designed and applied UFAD perimeter diffuser in action. The vertical pattern is limited to roughly 5 or 6 feet, at which point the smoke rolls back on itself. By limiting the height of the discharge pattern, this diffuser won't break through the stratification layer. Although light smoke can be seen above near the ceiling, it wasn't thrown to the ceiling. It simply rose due to its buoyancy. Several manufacturers now offer UFAD diffusers specially designed to provide perimeter solutions. Since perimeter loads are linear, it only makes sense to use a linear product. If a diffuser can handle the perimeter cooling load without need of a fan-powered terminal or booster box, that's obviously the way to go. These UFAD linear diffusers are available in actuated or non-actuated configurations and are designed to provide limited vertical projection. Here are some examples of UFAD linear diffusers in various applications. They provide a very clean appearance and can virtually disappear alongside exterior glass. Finishes can be coordinated to match window systems or floor finishes. This first photo shows a typical perimeter glass application with the diffuser running along the glass. The second photo shows an installation in an interior space running along a wall. And the last photo shows an installation in a raised windowsill. Several manufacturers offer UFAD perimeter heating devices. These are typically linear units designed to coordinate with UFAD linear diffusers. They contain fin tube elements that can provide either hydronic or electric heat. It's interesting to note that these devices typically do not handle any air supplied from the UFAD plenum. This means that they are heating devices and not reheating devices. We know reheat's a bad word. As you can see in this animation, the first thing that happens is cold air rolls down the glass. Then a wall-mounted thermostat or controller commands the heating unit on. Room air is drawn across the floor, into the grill, across the fin tube element, and then the warmer air naturally rises to cover the glass surface. UFAD projects provide many opportunities for achieving LEED certification. The partial stratification created by the UFAD system provides increased ventilation effectiveness and lowers the air volume requirements. The adjustability of the swirl diffusers provides personal comfort control without the expense of any additional controls. The higher supply air temperature and low pressure requirement of the UFAD plenum and the partially stratified environment result in energy savings. All of these features can help to achieve the following LEED credits under Energy and Atmosphere and Indoor Environmental Quality. For anyone interested in learning more about UFAD systems, ASHRAE has published 2 books on this topic. The original UFAD design guide was written by Fred Bauman, who works for the Center for the Built Environment at UC Berkeley. This publication was developed as ASHRAE Research Project RP 1064 and has been available since 2003. A few years later, ASHRAE put together a committee to update and expand the UFAD design guide based on new information and lessons learned. This committee completed their work and published the updated guide in 2013. This book is highly recommended. So to summarize what we've covered today about UFAD systems, air leakage can be a major issue if not handled correctly. Open offices are best handled with swirl diffusers. Common areas are best handled with swirl diffusers without regulators. Conference rooms are best handled with actuated diffusers or fan-powered terminals. Perimeter cooling is best handled with VAV linear diffusers. Perimeter heating can be handled by fan-powered terminals, but fin tube would be better. Perimeter diffusers must not disturb the stratification layer.